Good morning, everybody. Hello. Do you have any question from previous classes? Today we shall start a new chapter, crystal structure or crystallography. Before we start, if you have any question or doubts, please ask me from previous classes.
Sir,
Yes, please. Name, please, and then please ask the question.
sir, I am Sanskar. Actually, you told us you will inform us about the test this Wednesday, today.
I shall tell you, not Wednesday. I said it Friday exam, but this Friday meeting has been postponed to next Friday. So I shall take the normal class this Friday and the test will be carried out next week Friday. Means that will be 10th of September, Friday. So there will be no test on 3rd of September. There will be a test on 10th of September instead. During the class.
It will be a written test.
Yes. It will be a written test.
Okay, sir.
Any other question? If not, I start the chapter 3. In chapter 3, the issues that will be discussed are as follows. You know the solid composed of atoms in a periodic or non-periodic in nature. So how do these atoms assemble into solid structure? We shall mainly focus on metals, ceramics, and some electronic materials, not polymeric materials. From there, you can understand how does the density of a material depend on its structure and other properties. We will briefly touch on how do materials properties vary with orientation of atoms in a solid. So, how the atoms are packed? You assume the atoms are the solid sphere model, I mean just like assume table tennis balls. You put them together in this configuration. Sorry. You put them in this random configuration. You have voids in these areas, voids in these areas, voids in these areas, quite large, the voids. And we don't see any periodicity in their arrangement. However, if I put these atoms, spherical ball, in a regular packing fashion, you see how they are arranged. The size of this each hole is the minimum. In this region, it is very small. These holes are very small. So these are densely packed materials. These are loosely packed materials. These are densely packed materials. I do not know how to change the color of this pen. Otherwise, I would have changed it. But these white regions are the voids or space between the atoms. So in crystalline materials, the atoms are arranged in a periodic fashion in 3 dimensions. All metals, many ceramics, and some polymers are crystalline in nature. Here an example is given for the case of silica, crystalline silica. Quartz is a form of crystalline silica. Cristobalite is a form of crystalline silica, where silicon atom and oxygen atoms, silicon atom is red color, oxygen atom blue color. They are systematically arranged in a periodic way, filling up the 3-dimensional space. But the silica in sand or the window glass, the major constituents of your window pane is silica. There are sodium oxide, calcium oxide, and other oxides, but mostly silica. They are amorphous. The same number of silicon and oxygen atoms are there, but they are randomly arranged. Randomly arranged. There is no periodicity like here. You see, there is a periodicity in their arrangement. There is a periodicity in their arrangement. But we don't see any periodicity in their arrangement. So non-crystalline materials have no periodic packing or complex structures, or if you cool it from the molten state to room temperature or at an extremely fine rate. The random atoms in a liquid do not have sufficient time to take the position of regular arrangement of atoms in the corresponding solid. In that case, you form an amorphous solid. So amorphous material is non-crystalline. The window glass is made out of amorphous silica. They don't have a crystalline structure. Now I'd like to introduce to you an artist, a mathematician, a genius, to say, M.C. Escher. You can do a lot of search in the net and read about it. He was a graphic designer and the mathematician. Moritz Cornelis Escher, in a short form or commonly known as M.C. Escher. He was a Dutch graphic artist. He was born in 1898 and passed away in 1972. He is known for his inspired woodwork, lithography, mezzotints, various types of paintings, and this features impossible construction. I will show you some of the example, impossible construction, exploration of infinity, architecture, etc. Escher wrote his first paper, now publicly recognized, called Regular Division of the Plane with Asymmetric Congruent Polygons. Read this thing. Regular division of the plane with asymmetric congruent polygons, which detailed his mathematical approach to artwork creation. Means each of his artworks are being sold in auction for millions and millions of dollars. So his intention was to integrate mathematics into art. So Escher is considered as a research mathematician of his time because of his documentation with this paper which is mentioned above. He studied color-based division and developed a system of categorizing combination of, this thing important, combination of shapes, color, and symmetrical properties. This is quite important, these symmetrical properties. Why I'm saying this thing, you'll realize later on. In nature, in our universe, almost everything is symmetric. And with this concept of symmetry, what you are learning in third semester, later on in your career, whether you want to be a metallurgist, material scientist, physicist, chemist, you name it, the symmetry is the most important thing. The beauty of metallurgical and materials engineering program is that in post-graduation, you can go to any field of science and technology from here, or during people from other fields can do post-graduation in metallurgical and materials engineering, or in general, you say material science and engineering. Is there anybody in this class who does not know Sundar Pichai, the CEO of Google? Most of you heard of him that he is a BTech degree from IIT Kharagpur. Is there anybody who does not know that? Do you know which department he graduated from? Computer science?
Yes, sir. Metallurgy and materials engineering.
So what happened then? A metallurgical engineer became, huh? You see, there are examples, quite a few of those, who graduated from metallurgy department and became a superbly successful individual in varied engineering and scientific fields. One of them is Arun Sarin, who was the Chief Executive Officer of Vodafone Global, based in England. A few years ago, after making Vodafone a global brand, he left Vodafone and started his own company. Praveen Chaudhary, who was the Vice President of IBM, was also an alumnus of this department. So all these gentlemen and many more, I will tell you, were the alumni of our department. So MCSR, by studying these areas, he explored an area that later mathematician labeled as crystallography. So what he did, look at these figures, this kind of drawings. MCSR used to do that. You see, is there any area left in this figure which did not see a drop of color? Any of this figure? You see, he filled up the space with some drawings, colored ones, and there is no space in between. Look at this. I'm just from away, I'm drawing a picture. This feature looks like to me a tiny fish or tadpole. Tadpole means baby frogs. Looks like this. It has this brownish color. A tadpole has blue color. Another tadpole or this small fish has a yellow color. So he had brown, blue, and yellow. And the systematic way he drew it, it filled the entire rectangular area or almost a square area of this page. Do you see any relationship between these tadpoles? Anybody? You see
The
a
tadpoles
group.
of the same colors are parallel to each other.
Yes, that is true. The tadpoles of the same color are parallel to each other. But you see, you can make a group of or take a group of tadpoles of three different colors. Sorry, this one, this one. This should be removed. Each of them is an unit. You can look at it. Each unit is symmetrically related to the other unit. You can also see that each unit is symmetrically related to the other unit. If you look at this right side of the figure, I have three tadpoles, black, gray, and orange. They also are arranged in a symmetrical way. If you look at, three red tadpoles are meeting at this point. Here also, I am marking those points. Those points, you see, if I draw an imaginary tetragon, a rectangle, so each set of three tadpoles are touching four corners of the tetragon and a set at the middle of the tetragon. I can take black ones instead of these orange ones and get the same thing. I can take this gray color one and draw the same thing, I'll get this same rectangle. So he filled up the entire space by these drawings, and they are symmetrically arranged, means they have a pattern of repeating themselves in this drawing. If I move to the next drawing, you see the same thing. There is a pattern. If I move to another drawing of MCSR, you see the symmetry. Symmetry means these blue colored things at the center here, where they intersect, and these are at the four corners of the square and at the center. There is a symmetry. And individuals, lines and shapes are symmetrically arranged. You see this shape is arranged with respect to this, and this one has a symmetrical arrangement. You can take any pattern in this drawing, you will see the symmetry. They are symmetrically joined. There's a symmetry in the joining. Now you look at these pictures. Each white dot is an atom. These are atoms. Two atoms are closer to each other. As a group, they are existing. Do you see any symmetry in this atomic arrangement with this symmetrical arrangement? There is a pattern of repeating each unit. So these are the high resolution transmission electron micrograph of a sample where shows the regular arrangement of atoms in a crystalline structure. Regular means this periodicity in their arrangement. So the drawings of MCSR, you see the periodicity. Similarly, you see a periodic arrangement of atoms in solids. Any question? So, few definition. What is a crystal? So whatever you learned in your 11 and 12 and your coaching center like FitJE and others, please forget those things, where a lot of mistakes were made in explaining things as well as setting up the question paper. A crystal may be defined as a solid composed of atoms arranged in a pattern which is periodic in 3 dimensions. Periodic in 3 dimensions. Okay. This is important. Now, what is a lattice? You see, when a building construction is taking place, go outside, you see smaller buildings, they used to use bamboos. Now bigger buildings, they use steel pipes. A set of pipes parallel to each other are vertically mounted outside the building at the equal spacing, and similarly horizontal pipes are connected to these vertical pipes parallelly in a periodic arrangement. So there is a crisscross of these steel pipes and they are called lattice. If you open up any English dictionary, you will find out the meaning of lattice. But in crystal, lattice means a bit different thing. If you have only few atoms in a crystal, you can easily explain the atomic arrangement. You can visualize a model of a crystal, but if you have to explain to somebody how this crystal looks like quantitatively, you have to use certain mathematical terms. And here we are going to learn how we are going to mathematically explain a crystal. In thinking about crystals, it is often convenient to ignore the actual atoms composing the crystals and their periodic arrangement in space. If you have a complicated crystal structure, you have too many atoms, it will be difficult to explain the arrangement of each atom with respect to that crystal. So often, it is convenient to ignore the individual atoms. Rather, we should think about a set of imaginary points. A set of imaginary points, how they are arranged in a three-dimensional space. What I say by lattice is this: instead of considering each and individual atoms, how they are arranged in a three-dimensional space in periodic fashion, it is easier to imagine how a set of points, an array of points, are arranged in a symmetric way in three-dimensional space. These are imaginary points. Now, once we describe the arrangement of these points in three-dimensional space, I can take an atom or a group of atoms, assign them with respect to each point of those imaginary set of points. So let me explain again. Instead of considering all the atoms in a crystal at the beginning, we assume a set of imaginary points. How these points are symmetrically arranged in three dimensions, that we consider. Once we can define how these imaginary points are arranged in a three dimension, I assign atoms, a group of atoms, or an individual atom on these imaginary points or about this imaginary point. If I have a single atom, I can put it exactly on the point. If you have more than one atoms, I can club them as a group and assign each group about each point. So, a point lattice, a lattice consisting of a set of imaginary points which has a fixed relation in space to the atoms of the crystal, may be regarded as a sort of framework or skeleton on which the actual crystal is built up. Let me repeat it again. Instead of considering individual atoms at the beginning, we consider a set of imaginary points and how they are periodically arranged in three-dimensional space. Once we arrange these imaginary points in three dimensions, then we take an atom or group of atoms and assign them with respect to each point of this set of points. So if it is a single atom, it sits on the points. If it is more than one atom, they are arranged about that individual point. So we have first the imaginary arrangement of points, and then we assign atoms to each of these points. Any question? Is anybody there?
Yes, sir. Yeah.
Yes, sir.
Yes, sir.
Any question?
Yes, sir.
Sir, like if three group of atoms, can they be placed on one lattice point and then the
No.
same arrangement
If it
followed
is
on
one atom, you can put it in one lattice point. If it's more than one atom, you take a set and assign the set about that point.
So, sir, that group of atoms will take some number of lattice points and then the pattern will
Wait,
be
I will
repeated.
explain to you in
Okay.
with time. Okay. Now, how do you form this set of points? Imaginary points. I presume all of you are sitting in a room, not outside the house. At least one person answer.
Yes, sir.
Yes, sir.
Yes, sir.
Yes,
So
sir.
you are in a room. How many walls are there in your room?
4.
4.
4.
Okay. Wall.
4.
How many ceiling?
1.
1.
1.
How many floors?
1.
1.
Okay. So your room is defined by total number of surfaces. How many?
3.
6.
6.
Oh, sorry.
6. And 3 of them are the mirror image of the remaining 3. Means floor is the mirror image of the ceiling and 2 walls are the mirror image of the remaining 2 walls. But actually 6 surfaces. Correct?
Yes.
Yes.
So each of these surfaces, wall or ceiling, do they meet each other?
Yes.
Along a line, which is
Yes.
called the line of intersection.
Mirror images don't meet, sir.
Huh?
Mirror
Your
surfaces
walls,
don't
ceilings,
meet.
floors, do they meet any one of those? Each other?
The adjacent one meets.
Do they meet
Only
each
the
other?
Yes, sir. At the corner point.
they
Along
touch
what?
each other
Where do they meet?
at the boundary.
Along a line.
Yes, sir.
So how many lines like this you can create in your room?
8.
12.
12.
12.
12.
And these lines meet other lines. Where?
8 points.
Corner.
Points.
8 point. 8 point.
So in your room, you have 8 points. And assume each point is the point of a lattice. So this set of points can be formed as follows. Imagine space to be divided by 3 sets of planes. Actually 6, but 3 are just like a mirror image of the other 3. So you can call 3 sets of planes. The planes in each set being parallel and equally spaced. Assume your room is a cube. This division of space will produce a set of cells, each identical in size, shape, and orientation to its neighbor. So what is the smallest building block in your house? A brick, right? That is the smallest unit of your house.
Yes, sir.
You build the house using those bricks. So if you fill up all the rooms of your house by stacking bricks and don't leave any space in between the bricks, so your room will be filled up, and the smallest building block of your house is nothing but that piece of brick. You cannot reduce any further. A brick, if you break a brick, then it's a broken piece. But each brick is the smallest building block. So the division of space will produce a set of cells. A set of cells. each identical in size, shape, and orientation to its neighbors. So you are filling up your room with bricks aligned in a particular direction. So each brick has a shape, a size, and how it is arranged with respect to its neighboring brick. So each cell means each brick is a parallelepiped from the mathematical geometrical term parallelepiped. Since its opposite phases are parallel and each phase is a parallelogram. Now the space dividing planes. Space dividing planes. Now will intersect each other in a set of lines, just like the walls of your room I mentioned. And these lines in turn intersect each other as a set of points as referred above. So a set of points so formed, since in the previous slide what I explained, has an important property. What? It constitutes a point lattice. It constitutes a point lattice. One of you has your microphone on. I'm getting a hissing noise. Would you please switch off your microphone? So a set of points. Just one. A set of points so formed has an important property. It constitutes a point lattice. Don't mix it up. This point lattice is very important. Which set of points? Planes are intersecting each other along lines, and lines intersect each other at a point. So you generate a set of points. So a set of points so formed has an important property. It constitutes a point lattice. And a point lattice is defined as an array of points in space. Array of points in space so arranged that each point has identical surroundings. By which what I mean is this. If it is a physical classroom, I would have done this, but imagine you are sitting in a classroom. Each one has an individual chair and a writing tablet. Those chairs are arranged in periodic fashion in rows and columns. All of you are sitting there in your position. I go to an individual, say in the front row, stand in front of him or her and look at it in a particular direction. Say I look at the entrance door. If I look at it from that chair towards the door, I see how every chair is occupying the room. I get a view. Now I move to the third row at my left, stand in front of that individual and look it in the same direction, mean look towards the door. I get the same view of the arrangement of the chair. So I can move to any chair and look at a particular direction. It can be the door, it can be the window, always in the same direction, and I get the same view. So a point lattice is defined as an array of points in space. so arranged that each point has identical surroundings. And by identical surroundings, what I just said, we mean that the lattice of points, when viewed in a particular direction from one lattice point, would have exactly the same appearance when viewed in the same direction from any other lattice point, Please follow this thing very carefully. I repeat, a point lattice is defined as an array of points in space so arranged that each point has identical surroundings. By identical surroundings, we mean that the lattice of points, when viewed in a particular direction from one lattice point, would have exactly the same appearance, same look, when viewed in the same direction from any other lattice point. And this is called a point lattice. Never ever write crystal lattice. That is wrong. When we assign atoms to these points of the point lattice, we develop a crystal or a crystal structure. So nothing is called crystal lattice. That is a wrong term. There is something called a point lattice. Any question? Are you there?
Yes, sir.
Yes, sir.
Yes, sir.
How many of you there? Can you see the number?
Yes, sir.
How many?
Yes, sir.
Sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir. Sir.
Thank you.
Yes,
Yes, sir.
Yes, sir.
Now, you see, there is a three-dimensional space. This is the smallest building block, like a brick in your building. And this is the smallest building block. There are surfaces. They intersect each other along a line, and line intersects at a point. So this smallest building block has 8 points. And I stack this unit, smallest unit block, in such a way the three-dimensional space is filled up. So this three-dimensional space filled with a periodic arrangement of points in such a way there is not a single unoccupied space. So this smallest building block is called a unit cell, And the entire thing is called a point lattice. The entire thing, all the points here in this drawing is called a point lattice. The smallest building block, this one, is called a unit cell, the highlighted one. There are so many unit cells stacked. 1, 2, 3, 4, 5, 6. On the front surface I'm writing, then they are in the back side also. 8, 9. Then we have behind that, there's 1, there is another 1, there is another 1, there's another 1, and so on. And we can keep on adding more and more unit cells at the top, at the side, at the back, at the front. And you can fill up the entire space with this unit cell. And the previous unit cell the one highlighted here, number 1, I showed. Now it magnified and showed here. You will notice 3 things. This is the origin. You have 3 vectors. One vector along another vector and third vector. So vector quantity has a magnitude and a direction. This geometry of the unit cell can be defined by these 3 vectors A, B, and C. Their magnitude, length, will define the size of the unit cell, and the angular relationship between A, B, and C vectors, that is gamma, alpha, and beta degrees, will determine the shape of this unit cell. So these unit cells are defined by 3 vectors A, B, and C. The shape of the unit cell is defined by the angle between these 3 vectors A, B, and C, and their size is determined by the length of these 3 vectors A, B, and C. So the length of these 3 vectors and the angle between them, 3 angles between them, these 6 quantities, the lengths and angles between them, alpha, beta, gamma, are called lattice constants or lattice parameters. Lattice constant or lattice parameters, identical terms. So a unit cell is defined by these 6 lattice constants or lattice parameters. What are the lattice constants? A, B, C vectors length and the angle between them. Those 6 parameters define the shape and the size of the unit cell. And these 6 parameters, length of those 3 vectors and the angle between them, are called lattice constants or lattice parameters. Any question? So a unit cell is defined by the lattice parameters or lattice constants. So in dividing space by 3 sets of planes, we can of course produce unit cells of various shapes. So unit cell is defined by the length of those 3 vectors and angle between them. So by varying the length or the angle, we can grade the various geometries of the unit cell. But when we stack this unit cell like a smallest building block and try to fill up the entire space, there must not be any unoccupied space between the unit cells. Remember, I'm stacking the unit cells in 3 dimensions to fill up the space. But during stacking, I must not leave any unoccupied space between the unit cells. So the geometry of the unit cells will be such that I can stack them together and fill up the entire 3D space without creating an unoccupied space or space between the unit cells. So by varying the length and the angle of the lattice constants, various kinds of point lattices can be generated. However, you have to keep in your mind each unit cell. When we stack them together, they must not create an unoccupied space between the unit cells. So it has been found that 7 different kinds of cells, unit cells, can be generated, and they will not violate the definition of a point lattice. They will have the same view if you look at it in a particular direction from any of the lattice points, and there must not be any unoccupied space between the unit cell. So we can create 7 different geometries of the unit cells. And these correspond to 7 crystal, and this is important, systems, 7 crystal systems. All the crystals in the universe, not only our Earth, but the entire universe, must have one of those 7 crystal systems. And these things in the 1700, when these concepts were coming out, and this mathematician and philosophers came out with these concepts. They had no clue whatsoever about atoms and their arrangement. So these 7 crystal systems we can generate: cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. Any of those textbooks I refer to have these 7 crystal systems. I have taken this figure from the textbook Shackelford, which is the 3rd in your list, and these 7 geometries can be created. Now the bigger picture, you can see in cubic system, A equals to B equals to C, and angle alpha, beta, gamma all are 90 degree. And this is the unit cell I get of a cubic system. Whereas in tetragonal system, alpha, beta, gamma are all 90 degree, but one of the axes is not equal to other 2 axes. 2 axes A equals to B, but C can be bigger than A or B or smaller than A or B, not equal to A or B. That is tetragonal unit cell. In case of orthorhombic system, alpha, beta, gamma all are 90 degree, but neither one of them, A, B, C are equal to each other. So length, axial length, A, B, C will be different. In case of rhombohedral, A equals to B equals to C, just like cube, but alpha equals to beta equals to gamma. But unlike cubic system, this is not 90 degree. Here it was 90 degree, but here it is not 90 degree. That is rhombohedral system. In case of hexagonal, alpha, beta are 90 degree. These 2 angles are 90 degree, but gamma is 120 degree. A equals to B, but C is not equal to A or B. It can be bigger or smaller. But the unique thing that this is the unit cell of hexagonal. But does it look like hexagon? No. So in 11, 12, whatever hexagonal unit cell you have seen, actually that hexagon consists of 3 hexagonal geometry. What we drew consists of 3 unit cells of hexagon. And I will show you later on how an hexagon, the so-called quote-unquote hexagon, consists of 3 such units. Remember the word, unit cell is the smallest building block. Smallest building block. Highlight the word smallest. That is important, and I will show you tomorrow what I meant by smallest. In case of monoclinic system, A, B, C are not equal to each other. Alpha equals to gamma 90 degree, but beta is not 90 degree. And in case of triclinic, A not equals to B, B not equals to C, and alpha, beta, gamma none of them equal to each other and not even 90 degree. This is a unique case triclinic system with a very minimum symmetry elements that will be taught later on.
Sir, can you repeat what you have just said about hexagonal?
Hexagonal, if I draw, I'll show you next class. Draw a three-dimensional hexagonal body. Actually, it consists of 3 unit cells of this geometry. 3 stacked together makes an hexagon. So, definition of a unit cell is the smallest building block. So, this is the unit cell of a hexagonal system. And geometry equals to B but not equals to C, and alpha beta equals to 90 degree, but gamma is 120 degree. Let me see, I have a quick picture here or not. Just here, I'll show you. This is the hexagon you have seen in your book. Actually, it consists of 3 unit cells. This is an unit cell here.
Yes, sir, got it.
And this one is this, and the another one this. So these are 3 unit cells. I will explain to you later on. Just wait, my time is up. I shall take your attendance. Please wait.